In this video, we're going to look at some applications of the integral test. Part A, n equals 3 to infinity, log n divided by n. Part B, n goes from 1 to infinity, n times e to the minus n. So let's look at part A first. The corresponding function f of x is equal to log x divided by x. This function is positive and continuous for x larger or equal to 3. Let's show that. We know that log x is positive when x is bigger than 1, because when x equals 1, log x is 0, so when x is bigger than 1, log x is an increasing function of x, it cuts through the x-axis, and the y value is positive. And log x is also continuous for x larger than 0, because log x has a vertical asymptote at x equals 0. Therefore, the function f of x is equal to log x divided by x is positive valued. That means the y values are all positive, and continuous for x larger or equal to 3. But it's not clear that the function is decreasing. So we have to prove that. We're going to prove it by applying the derivative via the quotient rule. So we have f of x is equal to log x divided by x. Now differentiate this, f prime of x is equal to, applying the quotient rule, square the bottom, x times derivative of log x, derivative of top, that's 1 over x, minus the top, which is log x, times the derivative of bottom, which is 1. Simplify, and we get 1 minus log x divided by x squared. Now it's clear that the derivative f prime of x is negative when the numerator 1 minus log x is negative, because the denominator, which is x squared, is always positive. So let's make the numerator negative. 1 minus log x is less than 0. And we know x squared is always larger than 0. So making 1 minus log x less than 0, let's solve for x. That means 1 is less than log x. Exponentiate both sides, and we get e to the 1 is less than e to the power of ln x. And e to the power of ln x is equal to x. That means x larger than e. That means f prime of x is negative, or equivalently, f of x. Recall that if the derivative is negative, it tells us the function is decreasing. F of x is decreasing when x is larger than e. And to summarize, we've proven that the function f of x is equal to log x divided by x is positive valued, continuous, and decreasing for x larger or equal to 3. So notice it was decreasing when x is larger than e. E is 2.718, and the number 3 is bigger than e, so we can say the function is also decreasing for x larger or equal to 3. So now let's apply the integral test. Let's apply integral test. All the conditions are satisfied, and only now can we apply the integral test to find out whether this series converges or diverges. So we're going to apply the integral test to this series, summation n equals 3 to infinity, log n divided by n. This is the series that we're going to apply the integral test to. So we're going to choose the function to be log x over x, integrated from 3 to infinity. If the integral converges, the series converges. If the integral diverges, the series diverges. Let's do that. So let me write this as integral test. Let's make a title here. Integral test. All right, so integral from 3 to infinity, log x divided by x dx. This is an improper integral, so take the limit as p approaches infinity. Integral from 3 to p log x divided by x dx. This is equal to limit as p goes to infinity. Reversing the chain rule or applying U substitution, we get log x squared divided by 2, evaluated from 3 to p. So the U sub that we're applying is, let's label it U substitution. U is equal to log x. Differentiate du is equal to 1 over x dx. Alright, so we get limit as p goes to infinity. Applying the fundamental theorem of calculus, putting the upper limit in, we get log p all squared divided by 2 minus log 3 all squared divided by 2. Now, what is the limit of log p squared as p approaches infinity? Well, clearly log p is an increasing function of p, log x is an increasing function of x, log x squared is also an increasing function of x. So the limit as p approaches infinity of log p squared divided by 2, this goes to infinity. And so that means the improper integral diverges. So let's label that as diverges. So that means since the improper integral diverges, since the improper integral integral from 3 to infinity, log x divided by x diverges, then the series summation n equals 3 to infinity log n divided by n also diverges by the integral test. You have to state that, very important, because it's the integral test that determines that the series diverges. Because the improper integral diverges, the series diverges. That's what the integral test tells us. Also diverges by the integral test. All right, let's look at another example. Here we have summation n equals 1 to infinity n times e to the minus n. The corresponding function is f of x is equal to x e to the minus x. This function is positive. It's positive valued, positive y values. So positive. It is continuous. For all x, in particular, it will be positive and continuous for x larger or equal to 1. X larger or equal to 1. But it's not clear that the function is decreasing, so we're going to prove it by taking the derivative via the product rule. So f prime of x, let's take the derivative, applying the product rule, differentiate x, we get 1 times e to the minus x, plus keep x the same and differentiate the second term, we get e to the minus x times negative 1. Now let's factor out e to the minus x, multiplied by 1 minus x. Now it's clear that the exponential function e to the minus x is always positive. It's always larger than 0 for all x. So the only way that this expression f prime of x will be negative is if 1 minus x is negative. So f prime of x, the derivative is negative. That implies that 1 minus x must be less than 0. That means x has to be greater than 1. So we have proven that f of x is decreasing. F of x is decreasing on 1 to infinity. So let's apply the integral test to find out if this series summation n e to the minus n equals 1 to infinity, whether this series converges or diverges. So notice the conditions have to be met. The function has to be positive. We proved that x e to the minus x is a positive valued function. It has to be continuous. This function definitely is continuous for x and for all x, in particular for x larger or equal to 1, because we're starting our index at n equals 1. And then we had to prove that it was decreasing, and it wasn't so clear that this function was decreasing. So we applied a derivative. Recall, if the derivative is negative, it tells you the function is decreasing. We found the values of x for which this function was decreasing. We found the values of x for which this derivative was negative. And that was for x larger than 1, and we're starting our index at 1. So definitely this function is decreasing on 1 to infinity. All right, let's apply the integral test. So for the integral test, so let's label that integral test. All right, so we have integral from 1 to infinity x times e to the minus x dx. We're going to apply integration by parts, so integrate by parts. We're going to let u be equal to polynomial, u is equal to x. Differentiate, du is equal to dx, and dv is equal to e to the minus x dx. Integrate, and we get v is equal to minus e to the minus x. Because we're reversing the chain rule, the antiderivative of e to the minus x is e to the minus x divided by minus 1. So integral from 1 to infinity x times e to the minus x dx. This is equal to, this is an improper integral, so we have to write it as limit p approaches infinity, integral from 1 to p x times e to the minus x dx. All right, so applying the integration by parts, we're going to get limit as p approaches infinity. U times p, we get minus x, e to the minus x, minus integral v du, minus integral v, that's minus e to the minus x, times du, that's dx, evaluated from 1 to p, integrated from 1 to p, and let's simplify this, we get limit, p goes to infinity, minus x, e to the minus x, minus times minus is plus, and integrate e to the minus x. Another minus comes out because we're integrating e to the minus x via U substitution. So we get minus e to the minus x, all evaluated from 1 to p. Take the limit as p goes to infinity. Put the upper limit in, we get minus p divided by e to the p minus 1 over e to the p, applying fundamental theorem of calculus, minus, put the lower limit in, put 1 in, we get negative 1 over e, minus 1 over e. Now, we know that this is going to go to 0 because the numerator, which is p, rises a lot slower than the exponential function in the denominator. Because p is your linear function like x, so you're comparing y equals x, the linear function, to y equals e to the x. And if you look at a graph of that, e to the x, that's the 45-degree line through the origin, and e to the x is the exponential function, so you can see how the exponential function is rising a lot faster, so ratio approaches 0. And 1 over e to the p also approaches 0 as p approaches infinity, because the numerator is just a constant and the denominator is an exponential function, so ratio approaches 0. So the result is going to be negative times negative 2 over e, so the answer is 2 divided by e. That means the integral converges and has the value of 2 over e. All right, so we have limit, let's review that. Limit, p approaches infinity, minus p divided by e to the p, minus 1 over p, plus 2 over e. Now, we know that the exponential function, e to the p, is much larger than p. It grows much faster. For this reason, the limit as p approaches infinity of minus p divided by e to the p is equal to 0. And similarly, negative 1 over p, this ratio approaches 0 as p approaches infinity. So the limit as p approaches infinity of minus p divided by e to the p minus 1 over p plus 2 over e is equal to 2 over e. Converges. The improper integral converges. So that means the integral from 1 to infinity x times e to the minus x dx is equal to, this improper integral has a value of 2 over e. Anytime you get a finite answer for your integral, that means the integral converges. That's what convergence means. You get a finite answer for your integral, a number. Since the improper integral converges, since the improper integral from 1 to infinity, x times e to the minus x dx converges, then by the integral test, we can say that the series summation n e to the minus n goes from 1 to infinity, also converges by the integral test. You must state this, that it converges by the integral test. By the integral test. So basically the idea is we found in both of these questions, we looked at the improper integral and asked ourselves, we solved the integral and said, does it converge or does it diverge? If the improper integral converged, that means the corresponding series converged. And alternatively, if the improper integral diverges, that means the corresponding series also diverges. So that's how the integral test works. All right, thanks.